Hello, everyone. This is Eric Brown, along with Umberto Franier and Jose Martinez. Together, we're cohort members of FIU's TCN Broadband Wireless Network course. Today, we will be presenting our project, a literature survey paper on massive MIMO, small antennas, and space-time processing in wireless networks. As wireless networks have become more and more robust over the past decade, designers of these networks are constantly faced with challenges to improve their overall performance and efficiency. As a result, different approaches have been taken to maximize gains in these efficiencies within the wireless communication spectrum. One of the most recognized approaches has been the technology involving multiple input, multiple output MIMO antenna systems. However, with any new implementation, there are and have been challenges towards these implementations, such as with the rollout of the 5G cellular wireless network. In this part of the presentation, I will provide some background history on the MIMO and massive MIMO small antenna system, as well as some technologies that correlates in helping to improve the signaling communication in MIMO networks. Introduction and background. MIMO systems were first introduced in the 1970s. MIMO is often traced back to 1970s research papers concerning multi-channel digital transmission systems and interference between wire pairs in a cable bundle. ARK and D.A. George 1970, Brandenburg and Weiner 1974, and W. Van Etten 1975-1976. Although these are not examples of exploiting multipath propagation to send multiple information streams, some of the mathematical techniques for dealing with mutual interference proved useful to MIMO development. In the mid-1980s, Jack Saltz at Bell Laboratories took this research a step further, investigating multi-user systems operating over mutually cross-coupled linear networks with additive noise sources, such as time division multiplexing and dually polarized radio systems. Methods were developed to improve the performance of cellular radio networks and enabled more aggressive frequency reuse in the early 1990s. Space Division Multiple Access (SDMA) uses directional or smart antennas to communicate on the same frequency with users in different locations within range of the same base station. An SDMA system was proposed by Richard Roy and Born Arsteston, researchers at Raycom in 1991. Their U.S. patent number 5515378, issued in 1996, describes a method for increasing capacity using an array of receiving antennas at the base station with a plurality of remote users. Craig Raleigh's 1996 paper was first to propose a method for multiplying the capacity of point-to-point wireless links using multiple co-located antennas at each end of a link in the presence of multipath propagation. The paper provided a rigorous mathematical proof of MIMO capacity based on a precise channel model and identified OFDM as the most efficient air interface for use with MIMO. The paper was submitted to the IEEE in April 1996 and presented in November at the 1996 Global Communications Conference in London. Raleigh also filed two patent applications for MIMO in August of the same year. Raleigh discovered the multipath propagation could be exploited to multiply link capacity after developing an approved channel model that showed how multipath propagation affects signal waveforms. The model took into account factors including radio propagation geometry, natural and man-made objects serving as local reflectors and dominant reflectors, antenna array steering, angle of arrival, and delay spread. Bell Labs researcher Gerald J. Foschini paper submitted in September 1996 and published in October the same year also theorized that MIMO could be used to significantly increase the capacity of point-to-point wireless links. Bell Labs demonstrated a prototype MIMO system based on its BLAST Bell Laboratories layered spacetime technology in late 1988. I'm sorry, late 1998. Spacetime block code, also known as the Alamuti code, was developed by Siavash Alamuti and is widely used in MIMO OFDM systems. Alamuti's 1998 paper showed that the benefits of received diversity can also be achieved using a combination of transmit diversity and spacetime block codes. A key advantage of transmit diversity is that it does not require multiple antennas and RF chains in handsets. Massive MIMO is a concept that can be thought of as a large number of antennas, usually 32 to 64, used at the base station simultaneously to serve tens of users or mobile subscribers in the same time frequency grid. It's also a technology where the number of terminals is much less than the number of base station mobile station antennas. In a rich scattering environment, the full advantages of the massive MIMO system can be exploited using simple beamforming strategies such as maximum ratio transmission, maximum ratio combining, or zero forcing. To achieve these benefits of massive MIMO, accurate CSI or channel state information must be available perfectly. However, in practice, the channel between the transmitter and the receiver is estimated from orthogonal pilot sequences, which are limited by the coherence time of the channel. Most importantly, in a multi-cell setup, the reuse of pilot sequences of several co-channel cells will create pilot contamination. When there is pilot contamination, the performance of massive MIMO degrades quite drastically. To alleviate the effect of pilot contamination, a simple pilot assignment and channel estimation method from limited training sequences is proposed. However, in 2018, research by Emil Bjornson, Jacob Hodis, Luca Sanguinetti was published, which has shown that pilot contamination is soluble and have found that capacity of a channel can always be increased, both in theory and practice, by increasing the number of antennas. MIMO systems improve efficiency from using multiple transmitting antennas and multiple receiving antennas to increase the number of information channels within a wireless network in hopes of increasing data rates and signal quality being transmitted and received at the receiving antenna. To achieve this, we look now at some closely related technologies such as space-time block coding, spatial diversity, spatial multiplexing, and beamforming to see how these concepts come together to improve wireless networks. MIMO can be subdivided into three main categories: pre-coding, spatial multiplexing, and diversity coding. Diversity coding techniques are used when there is no channel knowledge at the transmitter. In diversity methods, a single stream is transmitted, but the signal is coded using techniques called space-time coding. Space-time trellis codes is an example of a space-time code. The signal is emitted from each of the transmitted antennas with full or near orthogonal coding. Diversity coding exploits the independent fading in the multiple antenna links to enhance signal diversity. Because there is no channel knowledge, there's no beamforming or array gain from diversity coding. Diversity coding can be combined with spatial multiplexing with some channel knowledge when some channel knowledge is available at the transmitter. Space-time code is a method employed to improve the reliability of data transmission in wireless communication systems using multiple transmit antennas. STCs rely on transmitting multiple redundant copies of data stream to the receiver in the hope that at least some of them may survive the physical path between transmission and reception and reception in a good enough state to allow reliable decoding. Space-time codes may be split into two main types: space-time trellis codes, distributed trellis code over multiple antennas and multiple time slots and provide both coding gain and diversity gain. Space-time block codes act on a block of data at once, similar to block codes, and also provide diversity gain, but doesn't provide coding gain. Space-time block coding is a technique used in wireless communication to transmit multiple copies of a data stream across a number of antennas and to exploit the various received versions of the data to improve the reliability of data transfer. The fact that the transmitted signal must traverse a potentially difficult environment with scattering, reflection, refraction, and so on, and may then be further corrupted by thermal noise in the receiver, means that some of the received copies of the data will be better than others. This redundancy results in a higher chance of being able to use one or more of the received copies to correctly decode the received signal. In fact, space-time coding combines all the copies of the received signal in an optimal way to extract as much information from each of them as possible. Beamforming, part of the pre-coding category, is the narrowest definition. In the narrowest definition, in more general terms, it is considered to be all spatial processing that occurs at the transmitter. In single stream beamforming, the same signal is emitted from each of the transmit antennas with appropriate phase and gain weighting such that the signal power is maximized at the receiver input. The benefits of beamforming are to increase the received signal gain by making signals emitted from different antennas add up constructively and to reduce the multipath fading effect. In line of sight propagation, beamforming results in a well-defined directional pattern. However, conventional beams are not a good analogy in cellular networks, which are mainly characterized by multipath propagation. When the receiver has multiple antennas, the transmit beamforming cannot simultaneously maximize the signal level at all of the received antennas, and pre-coding with multiple streams is often beneficial. Note that pre-coding requires knowledge of channel state information at the transmitter and the receiver. The next concept is spatial multiplexing. Spatial multiplexing requires MIMO antenna configuration. In spatial multiplexing, a high rate signal is split into multiple lower rate streams, and each stream is transmitted from a different transmit antenna in the same frequency channel. If these signals arrive at the receiver antenna array with sufficiently different spatial signatures and the receiver has accurate channel state information, it can separate these streams into almost parallel channels. Spatial multiplexing is a very powerful technique for increasing channel capacity at higher signal to noise ratios. The maximum number of spatial streams is limited by the lesser of the numbers of antennas at the transmitter or receiver. Spatial multiplexing can be used without channel state information at the transmitter, but can be combined with pre-coding if channel state information is available. Spatial multiplexing can also be used for simultaneously transmission to multiple receivers, known as space division multiple access, or multi-user MIMO, in which case CSI is required at the transmitter. The scheduling of receivers with different spatial signatures allows good separability. Spatial diversity falls under the diversity category. Spatial diversity employs multiple antennas, usually with the same characteristics that are physically separated from one another. Depending upon the expected incidence of the incoming signal, sometimes a space on the order of a wavelength is sufficient. Other times, much larger distances are needed. Cellularization or sectorization, for example, is a spatial diversity scheme that can have antennas or base stations miles apart. This is especially beneficial for the mobile communication industry since it allows multiple users to share a limited communication spectrum and avoid co-channel interference. This concludes my portion of the presentation. I will now hand the mic over to Umberto for his part.
To continue with this presentation, I will be covering three topics. The first one will be new challenges in wireless and free space optimal communications. The second one will be multiple input and multiple output systems and its benefits in the industry. And the third one will be how MIMO systems are designed and how they could impact different applications for different sectors. In this case, I will discuss the smart grid communication network. By using the standards for frequency allocation published by three different standard bodies, the International Telecommunication Union, European Conference of Postal and Telecommunications Administrations, the Inter-American Telecommunication Commission, and some information from NASA, we could determine that the main applications with the allocated wavelengths and the frequencies of major electromagnetic waves clearly shows that the spectrum is very congested and that there exists no room for new applications and services. As a side note, I would like to mention that only for SMS, which is a relatively new application for mobile phones, we have been able to generate benefits around 110 billion US dollars a year worldwide. This fact proves that the communication market is massive. According to The Independent, a UK newspaper, on Tuesday, 7 October 2014, there are officially more mobile devices than people in the world. The world is home to 7.2 billion gadgets, and they are multiplying 5 times faster than we are. Besides, customers become more exigent. Communication industries try to cope with the increasing number of customers and their high demand. This phenomenon is even without taking into consideration that many standard bodies are developing the fifth generation, which is commonly known as 5G. This generation should reach around 1 gigabytes per second and it should be adapted to handle the Internet of Things or IoT. The IoT is a major challenge for our communications networks. In fact, IoT will allow the communication among devices, which will be massively deployed in smart cars, smart roads, smart cities, and buildings. Also, it will be implemented for security and safety and industrial M2M communication. It is anticipated that in 2020 there will be around 50 billion connections according to Cisco. So 50 billion things will connect to the Internet of Everything in just a few years. The value this could create for service providers by 2022 is around 1.3 trillion US dollars, which presents the dilemma of the telecommunication industries, where the increasing of the customers' number will definitely impact the spectrum bands, which are already congested. A technology that promises enhancement in the achievable throughput and overall spectral efficiency is MIMO systems. The scarcity of the wireless spectrum is the main factor that hinders the vision for wireless access everywhere, anytime, and perhaps the toughest challenge that wireless research has to undertake. Overcoming this challenge requires innovations in various areas, including novel ways for spectrum sensing and reuse. As discussed in previous sections, mechanisms for using higher frequencies, such as wave, and generally more efficient protocols and systems. MIMO systems are one of the most promising technical advances in wireless communications in recent years. Such systems facilitate high throughput transmission in various recent standards, including LTE, WiMAX, WINR, among others. Space modulation techniques as space shift keying and spatial modulation are MIMO methods that use the multiple transmit antennas in an innovative fashion. Transmit antennas are considered as spatial constellation points and utilized to carry additional information bits to boost the overall spectral efficiency. Each antenna index is utilized to carry additional information bits and a special multiplexing gain of base to logarithm of the overall number of transmit antennas. Besides, activating single transmit antenna at a time eliminates inter-channel interference, relaxes inter-antenna synchronization requirements, reduces receiver complexity while allowing the use of a single RF change at the transmitter. To study the impact on this technology, we analyzed several applications use cases like the one presented in this slide. It has been shown that space modulation techniques enhance error performance with a moderate number of transmit antennas as compared to other conventional MIMO techniques. In addition, it is demonstrated that these techniques are more robust to channel imperfections, such as spatial channel correlation and channel estimation errors, as compared to other MIMO techniques, since the probability of error of space modulation systems is not determined by the actual channel realization, rather by the differences between channels associated with the different transmit antennas. To continue this presentation, I will hand the ball over to my colleague Jose, who is going to discuss another MIMO use case application. In this case, 5G towards energy efficiency, low latency, and high reliable communication networks. Thanks.
5G technology is expected to be operational by the year 2020. It is therefore crucial for us to know the direction of research and development in enabling 5G technology. In order to do so, we need to know the evolution of wireless technology and 5G's main goals. During the last 2 decades, the world has witnessed rapid evolution of cellular communication technologies. From 1G to 4G, the main motivation has been the need for more bandwidth and lower latency. Established in the 1980s, 1G brought us 2.4 kilobytes per second speed, which then led to 2G, which was established in the 1990s and brought us 64 kilobytes per second speed. From 2G to 3G, technology was advanced with higher network speed and faster download speed, which allowed real-time video calls. Then came 4G, which truly constitutes as a mobile broadband. Although 3G was the first mobile broadband standard, it was originally designed for voice with some multimedia and data considerations, whereas 2G was intended as the first digital mobile communication standard. From 2G to 3G, we saw an increased speed of 64 kilobytes per second to 2 millibytes per second. And 4G, which is 10 times faster than 3G, brought us 50 to 100 millibytes per second. 5G, which is the next generation, is expected to enhance not only data transfer speed and mobile networks, but also scalability, connectivity, energy efficiency of the network. The main goals of 5G. It is assumed that by 2020, 50 billion devices will be connected to the global IP network, which would appear to present a challenge. In a true network society, remote-controlled operations of appliances and critical commercial machines over a reliable 5G network will be possible with zero delay. Real-time control of machines by using mobile devices will be possible, making IoT more available to all. Finally, but not least important, less energy-hungry network nodes will be required towards a greener world. Therefore, the following are the most important elements in a description of 5G. Reduced latency, increased number of devices, better energy efficiency, reduced costs, and an increase of data rate up to 10 gigs per second per device. Through this, 5G will have a higher throughput, low latency, high reliability, increased scalability, and energy efficient mobile communication technology. Conclusion. To conclude, I'd like to give an insight of the advantages and the disadvantages of MIMO systems. Advantages are a better spectral efficiency at a low cost. MIMO drives greater bandwidth, reach, and spectral efficiency at a lower cost than alternative antenna technology. Its linear capacity growth. MIMO systems capacity grows linearly with the number of antennas. So 2x2 MIMOs doubles the capacity, as 4x4 quadruples capacity, and so on. It's backward compatible. It supports both TDD and FDD technology, so it can be used with earlier versions of 802.11 to increase data rate. The disadvantages of MIMO. MIMO has very few disadvantages associated with it. The disadvantages of MIMO system is mostly the need for multiple antennas, the cost of equipment compared to existing equipment available, and a limited open source driver support.